for the amazing talk. I had a question about essentially the locality of graph neural networks is interesting because I think there seems to be some problems if you were to rely on like long dependencies. So say, you have this locality constraint where you only learn from neighboring nodes. What if that's not enough? So say you have to perform message passing over, long dependency, obviously multiple edges. When you use like typical fixed architecture, say CNNs, and you use like attentional mechanisms like a non-local block, you typically can fix that. But for graphs, it seems that, that's kind of difficult, or at least it looks difficult. So what's your thoughts?
Yeah, thank you. This is a very important point, and I didn't have enough time in this tutorial to like properly cover it in great detail, but essentially it is a big problem to be able to quickly reach different parts of the graph, and pure locality might not be enough, but there do exist a lot of very standard approaches to deal with this problem in practice. One very common one is to introduce a master node, which is connected to every other node, and now suddenly the diameter of your graph is reduced to just 2. So you only need 2 hops to cover the whole graph. Of course, this might put a lot of pressure on the master node. So in reality, there's a lot of recent fun approaches that live somewhere in the middle, in the sense of having like nodes responsible for certain substructures like simplicial complexes and so on, and then passing data from the nodes to their substructures that then talk all to each other. So basically various more or less smart way of cutting down the diameter of the graph and making it more communicative seems to be a good way to persist the benefits of sparsity, but then at the same time to not have these issues. But thanks for raising that. It is a very important problem.
Any other questions? For the audience, you can talk here for the questions so the speaker can hear you better. So maybe Petra, you can also take some questions from the Zoom.
All right, yes. So let's see. Okay. Yeah, thank you all for the great comments. I would maybe start by, so there was a question on how to apply the geometric deep learning to Euclidean data. Yeah, this was actually one part that I did not have a lot of time to cover, unfortunately. In our book, we have a very nice part where we show how this all specializes to images. The idea is you can see an image as a sort of grid graph, which is endowed with coordinates. And now those coordinates actually matter. So you can encode basically translation equivariance by various combinations of circulant matrices, which specify all the convolutions. So it's basically a special case of a graph neural network where your edge connectivity comes from the locality of the image kernel. And also in this presentation, I also had some parts where we talked about, learning over manifolds and meshes, which I didn't have time to cover. But basically, you can also do learning over geometric graphs, like these molecules where different atoms have 3D coordinates. This is very important also for recent benefits in protein folding and these kinds of quantum chemistry papers as well. And one simple way in which you can use the geometric blueprint to enforce permutation symmetry, but also Euclidean symmetry, is by, for example, plugging the distances between the 2 nodes as an extra input into this message function. This is the essence behind EN equivariant GNNs that were recently published at ICML. So yes, there are many ways in which, you can use these ideas to deal with Euclidean data. Do you have any other questions from the live?
Yeah, I guess there are many other questions on that Zoom.
I'll answer one more. I'm assuming we should also make time for the next tutorial, right? But basically, there was one question that just came in on, do the 3 flavors have limitations to learning on graphs, or is there room to improving them? I'd say that's a very interesting open question in that probably there are different perspectives that will allow you to think about those flavors in a different way, like specialize the message function to be more mindful of certain symmetries or topological structure in the data. But from the point of view of the fundamental building blocks of graph neural networks, probably they are already expressive enough to cover everything you might ever conceive of. And I talk about this in my position paper on message passing all the way up that was recently published at an iClear workshop. But basically the idea here is you can get away with one hop local message passing to express pretty much everything, so long as you allow yourself to modify the structure of the graph before you do this. So everything kind of amounts to message passing, just the graph over which you're doing it might be potentially very different.